Hello everyone, myself Chris Murari, first year PhD scholar from CDFM group. In this video, I will be discussing about the assignment from our research writing course. Uh, what we have given in the assignment, we have to choose three papers from our field. Like I am from computational field, so I have to choose three relevant papers from uh, computational field, two from our group and one from a high impact journal like Nature Chemistry, JAX or EnguChem. And then we have to analyze the structure of the paper and check whether the introduction given in that paper is matching with the anatomy of the introduction section that we have taught in our course, and we have to discuss in what way it deviates from the uh, anatomy of anatomy that we have been taught in our course and whether it is good for clarity or not. Then we have to then we have to identify the discussion points and separate them from the results. And also we have to identify the use of reported result to compare the results given in the paper to give it a clear perspective. And in the last, we have to compare the abstract and conclusion section, how similar or different they are. So let's start. Uh, this is the anatomy of the introduction section that we have been taught in the that we have been taught in the course. So first, there should be broad introduction for a general audience, and then slowly we have to narrow then slowly introductions would be narrowed down to the your context, means to the relevant of the research paper, and then we have to mention some relevant previous works, and then we have to mention research gap or knowledge gap, and in the end what this research paper what you are doing in this research paper and for what purpose it is doing. So this is the general anatomy of the introduction section that we have been taught in our course, and we have to check whether this like anatomy of introduction section matches with the research paper, right? So this is the first paper. This is from Nature Energy. And this is about the selective visible light driven photocatalytic CO2 reduction to CH4 mediated by atomically thin copper indium sulfide layers. So if you will read this section, particularly this section I am talking about, uh, this can be, if you will read it line by line, then till here, uh, it can be considered as the broad introduction for CO2 reduction reaction. We all know how heavily we are dependent on the crude oil for our energy needs, and this is leading to the unprecedented increase in the concentration of CO2 in the atmosphere. Till today, the concentration of CO2 in our atmosphere is 430 ppm, which is at highest in past 8 lakh years. So CO2RR can be solution. So CO2RR can be a solution, and but CO2 reduction reaction can be a solution, but C double bond O, CO2 is a linear molecule, it's a stable molecule, and also these bonds, C double O bonds are very energetic, they have very high dissociation energy. So uh, photocatalytic CO2RR is a challenging process. It's not a easy one actually. What are the challenges associated with the CO2RR? First is like CO2RR involves various multiple proton coupled electron transfer process, and it produces various variety of products like carbon monoxide, methanol, methane, formic acid, and other products also, and higher hydrocarbons also. Um, Distribution of final product is usually determined by the kinetic and thermodynamic parameters of CO2 reduction pathway. For example, if you will see uh, the product that are obtained in the CO2 reduction reaction, they are some are thermodynamically favorable, whereas some are kinetically favorable. If you will see CO2 to formation of CH4, this has like lower potential, and CO2 to CO formation, this has like higher negative potential. So thermodynamically, CH4 formation is thermodynamically more favorable than CO formation because the former reaction takes place at a lower potential. But if you will see CO2 CH4 formation requires 8 electrons, whereas CO2 formation requires just the 2 electrons. So kinetically, CO formation is more favorable. So This is kind of, we can understand, is a broad introduction for CO2 reduction reaction. And slowly they are in this segment, they are talking about like the research gap. They have tried research community has tried various type of semiconductor catalyst like various metal oxides. They have reported for CO2 reduction, but still they suffer from two main problem. One is low conversion efficiency, and second is uncontrollable selectivity. So designing a highly active photocatalytic system with high selectivity for CO2 reduction uh, to any single product remains a huge challenge. So this is kind of we can think as of a research gap. This is general and broad introduction for CO2RR. This is kind of research gap. And now from in this part, uh, it's not actually the relevant previous work, it's the general relevant previous work, you can say. Like now they are moving on to the solution part. A typical CO2 photo reduction comprises of mainly three steps. One is photo adsorption, like visible light adsorption. Then there is charge carrier separation, and then there is migration of charge carriers to the surface of the photocatalyst, and then there will be CO2 reduction by photoexcited electrons. The first two steps, like photo absorption and electron hole separation, this photoabsorption and electron hole separation, charge carrier separation, they are related to the conversion efficiency. So first they have discussed about the problem, and then they are discussing about the solution, where the third mainly determines the final product selectivity, CO2 reduction by photoexcited electron. They like this will determine the final product selectivity, whether CH4 will form or formic acid will form or methanol will be formed. This is determined by the CO2 reduction by uh, a photoexcited electrons. Now, if you will see in this section, in this section they are discussing about developing visible light responsive photocatalyst. Developing visible light responsive photocatalyst is very vital, because visible light accounts for 43% of solar energy, and also for efficient uh, charge carrier separation. It is necessary to design defective semiconductor. What? Because the defect sites actually acts as trapping sites to capture photo-generated charge carriers and electrons, thereby enabling carrier separation. So this is very good for like photocatalysis. So uh, this is kind of like a general solution for the problems that they are facing. So this can be considered as the general previous relevant works for the CO2 reduction reaction. In this section, they are narrowing down it to their own context. With the conventional oxide or sulfoxide, with the conventional metal oxide or sulfoxide photocatalyst, uh, single metal metal side tends to bond weakly to the sole carbon or oxygen atom of the adsorbed CO2. This I can make you clear understand by this schematic. If there is a single metal atom side, then either carbon will bond to metal or oxygen will bond to metal, and then after just there is like single bond breaking between metal and carbon or metal or oxygen, then like various product will form, CH4 will form or CO will be formed. So like this is the general one. So what they are proposing, if there are dual active metal sides, so carbon as well as oxygen both can be connected to two different metals, and now in order to form like CO, you have to break this bond as well, this bond as well. So simultaneously breaking two bonds is like very difficult. It will be very energy demanding process. So CO formation will be not possible. And what they are proposing, and like if this is the scenario, uh, carbon as well as oxygen both are bound to two different metals, and then like successive protonation step, this will saturate the carbon atom, and this will lead to breakage of this bond, like weakening of this bond, and only this bond is like kind of breaking. Then after water will be released, like water will be released, and uh, then CH4 will be kind of released. So this is the like general context of their paper. So this is what they have discussed in this section. And now in this section, they are talking about what they have done. They are designing a single component photocatalyst that contain dual metal active sites as a model system for CO2 reduction to CH4. They have constructed atomically thin 2D layer to maximize the amount of dual metal site because of higher surface area per unit mass of the 2D polymer. And also they have created sulfur vacancy because these created defects contribute to increase in metal coordination and saturation degree. That will eventually help in mm, CH4 production. So this was the general introduction part. So we can broadly say that this is the like the introduction that they have given in this paper is more or less similar to what we have taught in the course, but uh, the order of the anatomy is slightly changing, but that is good for the like general understanding. So this introduction can be considered as a very good for any paper. So now moving on to the next points that we have to address in the assignment. So what they have done, they have created sulfur vacancies. They have characterized the sulfur vacancy using ESR. There will be peak in ESR, like due to the unpaired electrons, and that peak can be assigned to the appearance of sulfur vacancies. And now to understand the effect of sulfur vacancies on the electronic structure, they have performed DFT calculation, density functional theory calculations on the copper indium sulfide single unit cell, and like the presence of sulfur vacancy result in the charge transfer from other places to the surrounding copper and indium atom that lead to the charge enhancement of the copper or indium atoms near the sulfur vacancies. So this is the result kind of. You can understand this is the result. Like presence of sulfur vacancies is resulting in the charge transfer from other places to uh, surrounding copper and indium atom, and that led to the charge enrichment on the copper or indium atom. So this is the result, and like this is the discussion part. What that charge enrichment leads to. It is worth noting that the charge enriched copper and indium dual side may act as a dual highly active site to strongly anchor carbon and oxygen atom. So this is kind of to form a stable intermediate configuration, thus providing the possibility to tailor product selectivity. So this is kind of discussion. So this is the result, and like this is the discussion part. Moving on to the other part of the paper, here is also like uh, this is the result that pristine copper indium sulfide layer exhibited both CO and CH4 evolution with the rate like 1.3 micromole per gram per hour and 1.6 micromole per gram per hour, whereas the sulfur vacancy one the system in which there is sulfur vacancy, they achieve near 100% selectivity for CH4 production over CO evolution. Here, like both are producing CO and CH4 both are producing, but in case of sulfur vacancy, only one is producing. CH4 is producing, and it is producing with 100% selectivity. So this is kind of result, and like if you will read this part compared to other single component photocatalyst operating without sacrificial reagent and under similar conditions, the sulfur vacancy copper indium sulfide single unit layer exhibit a promising combination of high selectivity and activity for visible light driven CO2 reduction. This is kind of we can understand as a use of reported result to compare with the mm, uh, result that they are obtaining in their paper. Okay. Here also, if you will see, this is kind of result part, this is discussion part, like sulfur vacancy, copper indium sulfide layer as a contact layer of this much, which is smaller than the pristine one, and like what it is, like what kind of, what we can infer, what is the conclusion of that thing. This is like sulfur, a small contact angle means a higher surface hydrophilicity of the copper, sulfur vacancy copper indium sulfide layer, which favor water adsorption on their surface and possibility adding subsequent proton transfer, which is required for the CO2 reduction reaction. Right. So this is kind of result and this is part of discussion. Again, here it is kind of result and here what we are what we can be concluded from that. From DFT calculation, formation of CS a star COS intermediate is the rate determining a step for both the sample for pristine as well as sulfur vacancy. So and also this is a uh, sulfur vacancy single unit cell layer have a lower COS formation energy than the pristine one. So this is like result and what is the discussion? What is the discussion? Uh, this might be ascribed to the fact that introduction of sulfur vacancy is resulting in the charge enrichment in at the low coordinated copper and indium atoms around the sulfur vacancy, and the charge enriched copper and could serve as dual active site, and this will effectively stabilize the rate limiting COH intermediate compared to the single copper atom site in the pristine one, hence promoting catalytic activity. So this we can understand again as the there is some result and there is some discussion behind that. Similarly, here also, this is the result, this is the inference, and this is like kind of discussion. They are like saying that desorption energy of CH4 molecule on the sulfur deficient unit cell layer was much more negative, means it is much more exothermic than compared to the pristine one. uh, what is the conclusion from that thing? That CH4 desorption process is much easier and more spontaneous with the existence of abundant sulfur vacancies. This is kind of conclusion that we are getting from this result. And what is the discussion behind that? What could be the reason? So the reason behind that is the formation of CH bond in CH3O group cause the carbon coordination to be saturated and CH3 component to be separated from the surface of copper atoms in the sulfur deficient single unit layer, while the adjacent charge entries provide a perfect site for absorbing the unsaturated atom for the intense hybridization, and like this will be much more stable. So this we can understand again as the result, what we are uh, getting from that, what we are concluding from that, and again this is kind of discussion or the reason for that thing. So moving on to the last point of the assignment for one paper, that is we have to compare the similarities and difference between the abstract and conclusion. So first we will be discussing about the similarities in the abstract part. Both both abstract and conclusion both focuses on the same research problem. If you will think on both focuses on the same research problem, that is achieving high selectivity in the CO2 photo reduction. Both highlights the key catalyst design, uh, that is the sulfur deficient copper indium sulfide layer with copper in charge enriched copper indium dual side. Here also they are talking about the same charge enrichment of the low coordinated copper and indium atom. Both identify the central mechanism. If you will think about it, then they are talking about metal carbon oxygen intermediate. Here also they are talking about metal carbon oxygen dual metal intermediate. So both identify the central mechanism, that is formation of a stable metal carbon oxygen indium intermediate. Both explain the effect on reaction pathway, that is lower activation energy. If you will see lower activation energy barrier, here also it is they are talking about the lower activation energy barrier. They both like discuss about the conversion of endothermic protonation to exothermic endothermic protonation to exothermic protonation. Here also they are talking about endothermic protonation step 2 and exothermic protonation step. Both report the main performance result like 100% selectivity for CH4 production. Here also they talked about 100% selectivity for the CH4 production. Mm, and they also talked about the like yield, that is 8.7 gram micromole per gram per hour. So here also they are talking about the main thing. Both emphasize the importance of dual metal active site for controlling intermediates and selectivity. So eventually we can say abstract and conclusion both are more or less similar, but there are some difference that we will discuss here. Uh, difference. Moving on to the difference between abstract and conclusion. First, the like purpose and tone. For abstract, it's mostly about introducing challenges, approaches, and key finding. conclusion, it is more about summarizing result with a strong definitive claims. If you will if you will think here, then what is the difference? Like if you will see in abstract, there is no detailed techniques mentioned, experimental techniques mentioned. Whereas in uh, conclusion part, if you will see, this is like UV-based diffuse reflectance, SRPES, SPV, in situ FTIR, then SPUV, PIMS, and Gibbs free energy calculation. They are talking about the various experimental techniques and various validations. So this is for the first paper, and we will be moving on to the second paper. So this is the second paper, and this is from our group, and it discusses about the atomistic insights on phase-dependent functional properties, cadmium selenide nanocrystal. This is from our Kushal sir's paper. So let's discuss. So this can be moving on to the introduction part. We have to compare how the introduction given in this paper, like this research paper, matches with the anatomy that we have been taught. So first, this part we can consider as the broad introduction part, where they have discussed about the colloidal semiconductor nanocrystals and its use in the field of optoelectronics, like optical and electronic properties. And among various type of colloidal semiconductor nanocrystals, 2,6 semiconductor nanoparticles have been efficiently used due to their various properties, like they can be reproduced using solution-based synthesis. They are stable for a long period of time under operational conditions due to their narrow emission profile, facile tunability of photophysical properties, and also like they can be uh, developed in a semiconductor material core enveloped by ligand passivating surface or uh, another encapsulating cell, like core cell type of semiconductor, and this is like ligand passivated type of semiconductor nanocrystal. So due to these properties, colloidal semiconductor nanoparticles are very widely used, and also the quantum confinement effect minutely tunes the optical band gap and emission properties by manipulating the nanocrystal size. This is all about the general introduction of colloidal semiconductor nanocrystal, and this is like detailed atomic exploration demonstrate the surface of single crystalline has distinct facets. Now slowly they are moving towards the narrowing down to their context, like this paper is of facet dependent functional properties, so they are slowly narrowing it down, like surface of single crystalline colloidal nanocrystal has distinct phases and that can substantially impact crystal growth, ligand interaction, and overall physical properties. The most studied cadmium selenide quantum dot. This is the most studied colloidal nanoparticle, cadmium selenide quantum dot, and how careful selection of appropriate ligand during synthesis of nanocrystal can provide control over the shape and size of the facet. So this we can consider as the broad introduction part for the paper. And okay, now slowly they are now in this part, they are slowly narrowing it down to their context. There, they will be talking about passivation of undercoordinated selenium ions. So this is like earlier work, you can say. Several reports indicate that the passivation of undercoordinated anions can eliminate the mid-gap states of semiconductor nanocrystal. Also, inorganic salts offer various advantages over traditional long alkyl chain based in precise binding to receptor site. Less steric crowding on salt passivated surface also keeps it accessible to other molecular entities. So they are slowly narrowing it down to their context. They will be talking about the passivation of undercoordinated selenium, two coordinated selenium ions in this paper, and also they will be talking about how surface passivation can be done with inorganic salts like MCl, CDCl3 and CDCl2 and MCl3, Indium chloride. So they are slowly narrowing it down to their context in this part. And now, like this is the report of this is a relevant previous work. So you can clearly see here, Potep and et al. Demonstrated that the electronic properties of zinc blende of cadmium selenide nanocrystal can be tuned only through jet tap ligand displacement. Such ligand loss introduces mid-gap state. Then Stanipe provide ATL provide insights into the non-radiative recombination process that severely limit to the use of zinc blende cadmium selenide nanocrystalline energy conversion schemes. So one there is one more relevant previous work that like Ridgeworth at L depict the heterogeneity in the binding affinity of ligand on zinc blende cadmium selenide nanocrystal surface. Now this is the research gap. What what is missing till now? So the largely the distinct roles of facet polarity on defect state positions, optoelectronic properties or characteristics, and the catalytic properties of cadmium selenide nanocrystals have not been yet thoroughly examined or explored. Moreover, detailed comparison between the electronic properties of similarly sized cadmium selenide nanocrystal with two different phases, like zinc blende structure and Urgite phase structure, is yet to be investigated under the impact of the crystal phases at the nanoscale. And now, in this part, they are discussing about what they have done and for what purpose they have done. In this study, they have modeled less explored metal-rich Urgite phase cadmium selenide nanocrystal. Zinc blende phase is the studied one, so they have a model relatively less explored Urgite phase one, and they will try to understand the facet-dependent photophysical properties on these Urgite nanocrystals. And they will also discuss about the surface passivation using inorganic salts like CdCl2 and indium chloride. They how efficiently eliminates the selenium-based localized trap states and exhibit facet delocalized frontier FMOs, and the polar facet dominantly delocalize the frontier molecular orbital. Like they will discuss about these things. And also they have computationally simulated optical absorption spectra for the cadmium selenide nanocrystal, and in the last they have studied about the HER on the cadmium selenide nanocrystal. So you can clearly see this is kind of broad introduction part about the colloidal semiconductor nanocrystals, their properties, how what are the types like ligand precipitated and core cell quantum confinement effect, and like cadmium selenide is the most studied one. So and here they are narrowing it down to their context like passivation of under-coordinated anions and by using inorganic salts like CdCl2 and indium chloride. And these are the reported previous works they have mentioned. And like this is what they have done for. So this is in the same way that we have been taught in our course. So this is relevant. Now moving on to the result and discussion part. So we can clearly see this is kind of result. The average cadmium selenide bond length in the optimized nanocrystal. So first they have taken the unoptimized crystal structure nanocrystal, then they have optimized, and then they have found out the bond length, and then they have found that these are 2.62 and 2.69 angstrom. And this surface bond contraction, like you can see the surface bond is like lesser as compared to that of core one. So why there is like less surface bond? Like surface bond is why smaller. Uh, so they align with the like surface bond contraction with the previous result. So you can clearly see like this is the result and this is the use of the reported result to uh, give a your result a clear perspective and a proof also. So there is one. This is also this part we can think of. This part we can think of the results like projected density of a state exhibit the HOMO is primarily contributed from selenium 4p orbital, whereas the LUMO is comprised by 5s orbitals of cadmium with along with selenium, 5s orbitals of selenium and 5p orbitals of selenium. And like this is the band gap 1.99 electron volt. This is kind of result part, right? And like this is the discussion part. What can be inferred from that HOMO composition of HOMO and composition of LUMO and like band gap. So here they are talking about the non-bonding orbital create localized in-gap states and can act as efficient trap state. This is more or less kind of a discussion part. Okay. Due to time constraint, I will not be able to highlight each and every result and discussion part. So it's just a like introductory part. Here also, if you will see the metal salts like indium chloride and cadmium chloride effectively efficiently passivate the two coordinated selenium atoms by forming a stable metal selenium bonds where and the average bond lengths of metal selenium are this. So this is kind of a result part, and this is what the discussion part, how those things are helping in anything. Like if you will read about it, you will get the idea. Moving on to one of the important result of this paper. Here they have investigated the catalytic activity of cadmium selenide metal-rich cadmium selenide nanocrystal for HER on both polar facet as well as non-polar crystal facet. This cadmium selenide nanocrystal have various types of facet, polar facet as well as non-polar facet. So what they have done, they have studied HER on polar facet as well as non-polar facet. So if you will see, this is kind of adsorption energy for hydrogen on uh, selenium sites, that is centered edge and vertex site selenium on the uh, polar facet, that is 0001 bar. This is kind of HOMO. So there you can see adsorption energy for hydrogen is negative on the selenium center facet. So this is the result, and what they have like, why that is kind of exothermic or negative. So this is the like discussion part. The delocalized electron density at the middle of the facet, like on the center selenium site, facilitated the hydrogen adsorption process, catalytically boosting the HER. The lack of charge density at the edge or vertex of this facet causes an endothermic adsorption for the same reaction process. So this is kind of result, and this is the discussion part of that thing. Here also, they have talked for the, like this is for the 000. If you'll see, this is for the 0001 facet, and on the next page, this is for the 0001 facet. That was for 0001 bar facet, and this is for 0001 facet. So this is the kind of result, and how they have like, this part is inference or like use of previous results to explain their results. Uh, So you can clearly see like the following the from the following the Sabatier principle, we recognize the best catalytic facet should have an intermediary binding strength for hydrogen atom, both strong and both weak. That is like Sabatier principle. This is another result you can say from another paper, like, and that is used for describing the result of this paper. So now in the last, we will be discussing about the comparing the abstract and conclusion part. What are the differences and what are the similarities between them? First, we will discuss about the similarities between the abstract and conclusion. First thing is that both sections focus on the same central theme, like facet dependent electronic, optical, and catalytic properties of the cadmium selenide nanocrystal. Similarly, here also they are discussing about like facet dependent ligand surface interaction and their impact on the optoelectronic and catalytic property of the cadmium selenide nanocrystal. Both abstract and conclusion highlight like identify the origin of trap state. Here you can see uh, localized trap state due to under coordinated selenium atom. Here also two coordinated under coordinated selenium atoms and whole trapping state. Like this is the origin of the trap state. Both highlight the role of the surface passivation. Like here also, like in blue color, if you'll say the inorganic salt selectively bind and passivate these anionic site, like two coordinated selenium site, effectively efficiently mitigating the trap state. Here also they are discussing about the binding affinity of metal chloride salts to anionic states. Anionic site significantly depends on the initial control. Like this is also the metal chloride salt that they are talking about, that is same as CdCl2 and indium chloride. Both emphasize the band edge behavior. If you will see that like this red part mostly delocalized band state, HOMO and LUMO states delocalized only over the polar surface. So this is the one. So these are kind of some similarities between the abstract and conclusion. And if you will discuss, uh, see the like difference, there is not much difference, but like the difference between abstract and conclusion is like in abstract we give a broad overview, introduce problem and key finding, and in conclusion we like provide detailed summary with a stronger, more definitive claim. Like in here abstract part, we have generally mentioned like facets and effect. We don't have mentioned which facet or like which specifically which facet. So we have like simply mentioned the facet. Here we are mentioning the polar facet and non-polar facet. Like this type of facets we are mentioning a specific one. Like here only we have mentioned site dependent behavior. He will in this conclusion part we will be talking about uh, selenium center, selenium edge, and this kind of properties. And if we will talk about one more difference, that is uh, in abstract part, regarding the catalytic insight, we have like we have given us the mm, general statement about the catalytic relevance, like the location of active atomic site and facet polarity further play a catalytic critical role in their catalytic performance for HER. But in here, we are mentioning which site, like negatively charged polar facet, demonstrate the superior performance as a catalyst for HER. We are specifically mentioning the site as compared to other polar and non-polar facet. So this is it for the second paper, and now we will be moving on to the third paper. So moving on to the third paper, this is hot electron driven to nitrate to ammonia conversion of nanocatalyst insights from quantum dynamics simulation. So moving on to the introduction part. So this part we can think of as a broad introduction, broad context. Uh, in this paper, we are talking about nitrate to ammonia conversion on nanocatalyst. So first, what is the need for nitrate conversion? One reason is that nitrate contamination in groundwater system poses a critical environmental challenge, and like uh, high concentration of nitrate in water can cause various diseases. So that is one reason we have to convert nitrate into something less harmful. And also, if we can convert nitrate into ammonia, then we all know ammonia is used as a mm, raw material for fertilizers in fertilizer industry. So it will like possess dual benefit. First, harmful nitrate ion is removed, and secondly, it will be converted into ammonia. First, one more thing is that conventionally ammonia is produced through Haber-Bosch process, and like this process demands extreme condition like temperature greater than 400 degrees centigrade and pressure greater than 200 atmosphere, and this consumes 2% of global energy. So this we can consider as a broad context. And now electrochemical conversion nitrate. Now this was like kind of problem statement, and this is like solution. Electrochemical nitrate to ammonia conversion offers a promising ambient condition alternative, right? So one alternative is like electrochemical nitrate to ammonia conversion, then photocatalytic strategies for nitrate to ammonia conversion, and this is kind of solution. Like we can think of as a general work or current state of research, what it is going on. Then like photocatalytic strategies for nitrate to ammonia conversion. Now these are kind of problems in photocatalytic strategies for nitrate to ammonia conversion, like rapid charge recombination, insufficient semiconductor reactant interactions, limited mechanistic insights into the photo-induced pathway. So this is kind of a problem. So uh, one more technique you can say, like hot carrier catalysis has emerged as a advanced strategy. Uh, these are some benefits of that hot carrier. Generally, the faster hot carrier extraction from the catalyst to the reactant species, it actually boosts the photocatalytic conversion rate and product selectivity. Now, this is the problem with the hot carrier relaxation, like phonon bottleneck. And like for that, cadmium selenide, quantum dot are among the most promising catalyst on the reason behind that is like they have tunable hot carrier relaxation. So this we can understand as a broad context, and this is like general work or current state of research that is going on in the research community. Moving on to the next part, like uh, now this is the research gap. Despite significant interest, a comprehensive understanding of hot electron-induced nitrate reduction at semiconductor molecular interface remains largely incomplete. So, hot carrier catalysis is a very good alternative, but still it suffers some problems. Like there is mm, a lack of understanding of molecular interfaces, how they behave. And now moving on to the last part, like this part, what is done in this paper and for what purpose it is done. Like in this paper, uh, we will be providing a computational insight into the hot electron mediated nitrate to ammonia reduction on ligand passivated, actually halogen passivated metal rich cadmium selenide quantum dot surface using AIMD, ab initio molecular dynamic simulation, right? So this is like what is done in this paper and what is the purpose for doing that. So in this paper, earlier in the both paper that we have discussed, we were seeing that results and discussion were included in the same part. In this paper, result part is different and discussion part is different. So we will be discussing that part. Result part, if you will see, like this part, if you will go through, this is a static geometric details. This part is a static electronic details like valence band, mm, homo lumo, what is like homo lumo comprising of like which orbitals are contributing in homo lumo, what is the band gap of the conductor, like and absence of mid gap traverse states. So this has been discussed in this part, right? And also the like in this part they have discussed about the adsorption configuration, adsorption like NO3 binding of NO3 on the opposite phases. What are the modes of the binding? Like here it is, if you will see it, here it is chelating, if you will see tilted and chelating binding mode. So this is the result part, and in result part, if you will see like how result and discussion parts have a little bit of discussion has been oriented. Uh, this you can think of a like previous work that is used in used to give it a clear perspective, like hot electron cooling in quantum dot nitrate system may occur through two primary process. One is through carrier relaxation through involving NO3 molecular state, where initial hot electron density is transferred to first to the LUMO of the nitrate molecule, then it will be transferred to the low-lying conduction band states of the quantum dot. Second is direct relaxation of hot electron to the conduction band maxima of the quantum dot without involving the closely spaced absorbed state. Note only the formally pathway like hot carrier relaxation through involving NO3 molecular state is favorable for molecular photoreduction. Here, like electron transfer from quantum dot state to the molecular states is faster. These are kind of results, and to justify that, they have used up another previous work like non-adiabatic coupling values. Faster the coupling values, like higher the coupling values, faster the electronic transition between the states. Here you can see the coupling value with for CBM plus 2 and CBM plus 1 is very high, like 14 milli electron volt, whereas for CBM plus 2 and CBM it's 1.8 electron volt. So the transition from CBM plus 2 to CBM plus 1 will be significantly higher or stronger, whereas electronic transition between uh, CBM plus 2 and CBM, it will be significantly lower because on the NAC value, non-adiabatic coupling value is 1.8 milli electron volt. So this part you can think as of a result part, and this part is a kind of discussion part that I have just discussed. Like NAC between CBM and CBM is significantly weaker, 2.6 milli electron volt, suggesting slow hot electron cooling from molecule back to the quantum dot. So this is kind of discussion part. And also here one model is used like impulsive two-state framework. This is also like previous work you can think of, and this has been used to like give a clear perspective to the what we have done in this paper. So if you will see, like this is impulsive two-state model that mimics the photo excitation of the adsorbate by injecting a single electron from quantum dot core to the NO3 molecular state, and then in excited state, molecule will evolve over a time for a few femtoseconds on anionic excited state potential energy surface before it returns to the ground state potential energy surface. Like this is the previous reported result, and this has been used to justify the result in of our paper. If you will think like I can make you understand pictorially, mm, this is excitation of bending mode. You can think of like there is a variation in the bond angle of like uh, three type of angles are defined between NO3, theta, phi, and alpha, and this like denotes the variation of angles. If you will here see, here there is yeah, this is bond length variation with time, and you will clearly see there is much more fluctuation in one NO bond length as compared to that of NO other two NO bonds. So at time, if you will see tau is equal to 25 femtosecond, like this is the length of the, this is excited state time scale, you can say, carrier lifetime, like excited state lifetime at t is equal to 0 femtosecond, it's like this one. As the time increases, like at t equal to 25 second, you will see NO3 is kind of getting dissociated into NO2 plus NO. And finally, this will be like NO2 will be binded and it will be separated from NO. Same thing will be happening for, if you will see for NO2 as well. NO2 is getting kind of dissociated into NO plus O. If you will see here it is NO2 and here NO and oxygen are separated. So impulsive two state model is kind of mm, used to study the dissociation of first NO3 into NO2 plus O and then NO2 to NO plus oxygen. Like, so this is a very important result. And also then after they have described NO will reabsorb on the surface of the quantum dot. See here NO will be NO is getting reabsorbed on the surface of the quantum dot. Then further successive protonation will kind of lead to the formation of ammonia, and then ammonia will dissolve on the from the surface of the catalyst. So this was kind of results, and here it is the discussion part. A sequential photoactivated reaction pathway NO3 to NO2 NO that I have just discussed, initiated by consecutive UV visible photon excitation with thermodynamic feasibility, and like this is the ammonia formation part that I have uh, just discussed earlier. Relevant, this is kind of previous results that are supporting. Relevant experimental study also supports the feasibility of an hot electron driven pathway. This is in plasmonic system, how hot electron injection is linked to enhanced photocatalytic activity like nitrate to ammonia conversion. Now, this is the impulsive use of a impulsive two-state model for uh, NO2 to NO conversion. So this is one more use of reported result. Chua et al. Imply excited state dynamic to depict the surface oxygen vacancy, not the under coordinated titanium side. So this is one more similar ultra fast. So these are the use of various reported results. This one is also more one more. So these are the use of previous results to explain the our results, yeah, results given in the paper to give it a clear perspective. Now moving on to the last part, and that is like comparison of abstract and conclusion. Like both the abstract and conclusion communicate the same central scientific message. That is, they describe how hot electron generated in cadmium selenide quantum dot are transferred to the nitrate molecule, specifically into its LUMO, which act as primary electron acceptor. In both sections, it is highlighted that nearly 70% of the hot electrons are captured by nitrate. Here you will also see, and this leads to the formation of transient NO3 dynamic NO3 anionic state. This you can see, and uh, both also agree on the key reaction pathway where NO3 first dissociates into NO2 and oxygen, and then further NO2 to O, and in both the process you can say like presence of key local surface geometry, like presence of under coordinated surface cadmium center is very important to excite antisymmetric vibrational stretching mode as well as bending mode. Here also you can see key role of surface symmetry, particularly the presence of under coordinated three cadmium three coordinated side. Moving on to the like difference part, the abstract is a kind of concise summary. It provides the problem statement, method use, uh, and the key finding, but it does not go into the detailed explanation of how the reaction proceeds. In contrast, conclusion provides a deeper mechanistic understanding. Like in here part, if you will see, in conclusion part, we are discussing about the vibrational excitation, hot electron trapping, that we uh, discuss in the abstract part to a lesser extent. Another key difference is that The abstract gives a broad conclusion suggesting improved catalyst design, where while the conclusion provides a specific design insights emphasizing how surface structure controls the reaction pathway. So that's it for the this video.